Okay, so if you're an engineering student and you're staring down this massive lab sheet full of material properties, totally wondering how to keep them all straight, well, you are in the exact right place. Welcome to this explainer. Today, we're basically building your ultimate cheat sheet for decoding complex mechanical properties. We're going to strip away all the overwhelming textbook jargon and look directly at what makes metals bend, break, stretch, and most importantly, survive. Think of this as your survival guide to the anatomy of a material. Let's get into it.
Take a look at the date on this metallurgical analysis textbook cover, 1947. I know, ancient history, right? But here's the thing. While the tech we build today evolves at absolute lightning speed, the fundamental physics we're decoding here, they remain exactly the same. The principles of how materials behave under loads, the very same principles evaluated by engineers literally decades ago, are the exact same ones you're going to use to design tomorrow's mechanical systems.
Here's our quick roadmap for this explainer. 1. Basics, stress and strain. 2. Elasticity and Hooke's law. 3. Tension versus compression. 4. Ductility, brittleness, and toughness. 5. Surviving sudden impacts. And 6. The long game, fatigue. All right, let's kick things off. Section 1. Basics, stress, and strain.
So, what do we actually mean when we talk about the strength of a material? Basically, it's just a material's ability to withstand loads, to resist mechanical forces. And this brilliantly illustrates a fascinating fact from our source material. If you were to test a perfect single crystal of metal, its strength can actually reach around 1,000,000 pounds per square inch. I mean, that's wild. That exceeds the strength of ordinary polycrystalline metal by 100-fold. But of course, the real-world metals you'll actually work with aren't perfect crystals, and that is exactly why we have to measure and test them so rigorously.
And that brings us to the ultimate duo, stress versus strain. Now, stress is the internal balance of compressive and tensile forces within the metal itself. Our sources highlight that you can actually see internal stress indirectly through things like springback, which, if you don't know, is when a rolled strip of metal increases in diameter after being removed from a holding mandrel. Strain, on the other hand, is the physical result of that stress. It's the actual elastic or plastic deformation of the material. Think of it like this. Stress is the invisible load, while strain is the visible distortion. Moving right along to Section 2, Elasticity and Hooke's law. Our source provides this super fundamental quote. Hooke's law states that in elastic materials, stress is proportional to strain. So what does that mean in plain English? It means that as long as you're within a material's elastic limit, the amount you pull or push it, the stress, will result in a perfectly proportional amount of stretching or squishing, which is the strain. It is literally the core rule of stiffness and rigidity.
And this leads us right to the formal definition of elasticity. Elasticity means that the strain, or the deformation, is present only while the stress is being applied. Once you let go, boom, it snaps right back. We measure this stiffness using what's called the modulus of elasticity. So the absolutely crucial point here for your future designs is this. The modulus of elasticity is an inherent measure of stiffness, and it is not appreciably affected by heat treatment. If you design a part and it turns out way too springy in its annealed state, you can't just heat treat it to fix the modulus. You actually have to pick an entirely different material.
Okay, Section 3, Tension versus Compression. To find a material's true limits, engineers constantly pit tensile strength against compressive strength. Tensile strength is a material's resistance to being pulled apart. Think of stretching a rubber band until it finally snaps. Compressive strength is the exact opposite. It's the material's ability to withstand being crushed or squeezed under a really heavy load. And, when a material just can't take it anymore, it reaches its ultimate strength. This is the definitive peak load. It's the specific stress necessary to completely break a standard specimen. For example, our source notes a standard steel specimen that hits its ultimate strength right at 85,000 pounds per square inch. Once you cross this line, you aren't just getting deformation anymore. You are getting catastrophic failure. Game over for that part. Let's dive into Section 4, Ductility, Brittleness, and Toughness. First up in this trio is ductility, which is often measured as elongation. This is simply a material's ability to stretch, bend, or flatten out without fracturing. If you put a highly ductile material under massive compressive strength, it won't necessarily shatter into 1,000,000 pieces, it'll just flatten into a pancake. It's kind of nice because it gives you plenty of physical warning before things go completely wrong. Now, compare that to brittleness. Brittle materials are the exact opposite of ductile ones. When a brittle material hits its limit under compressive or tensile stress, it doesn't stretch, and it definitely doesn't flatten. It just snaps. It fractures cleanly and super suddenly, no warning whatsoever.
Alongside those breaking points, we also have to evaluate hardness. This is a totally crucial mechanical property that specifically measures a material's resistance to surface deformation, scratching, or penetration under a load. It's very often evaluated right alongside the breaking points to determine just how durable a material's exterior is against everyday wear and tear.
And then we have toughness. Honestly, toughness is the brilliant middle ground. It's closely linked to impact strength and indicates a material's ability to absorb energy and deform plastically before actually fracturing. It essentially bridges the gap between just having high ultimate strength and actually being able to take a severe hit in the real world.
Which brings us to a really major question for any engineering student. I mean, it's one thing to test a metal by slowly, carefully pulling it apart in a nice, quiet lab. But how does a material handle a billion tiny vibrations over 10 years versus one giant sudden hit?
That brings us to Section 5, Surviving Sudden Impacts. To survive that giant hit we just talked about, a material absolutely needs impact strength. This is a dynamic property measuring a material's resistance to suddenly applied loads, and it's heavily dependent on the delicate balance between toughness and brittleness. And guys, here is a staggering statistic from our sources. An estimated 95% of all metal failures in machine parts are caused by dynamic loads. 95%. That means mastering impact strength and dynamic properties isn't just like extra credit, it's practically the whole job.
Finally, we've reached Section 6, the long game, fatigue.
Let's take a quick look at this comparison table. On one side, we have static properties, like the tensile and compressive strengths we discussed earlier. These measure steady, constant loads. But on the other side, we have dynamic properties, impact resistance, fatigue, and damping capacity. Damping capacity, by the way, is a material's ability to dissipate vibrational energy as heat and sound. In the real world, you have to remember your materials aren't just holding dead weight. They are constantly bouncing, vibrating, and pulsing.
So when we talk about those pulsating loads over time, we really have to define fatigue, and specifically the endurance limit. This is the stress level below which a material will absolutely not fail, even if subjected to an infinitely large number of stress cycles. To figure this out, metallurgists use something called a rotating beam method. They take a polished specimen, spin it rapidly while holding dead weights, and subject it to alternating tensile and compressive stresses millions of times until they find that perfect, safe limit.
And finally, there's creep strength. Creep is the slow, time-dependent distortion of a material under a constant load, especially at really high temperatures. Our sources give a great example for this. Imagine a steam turbine operating over 100,000 hours. Design engineers must choose working stresses so that the creep remains within a tolerable limit. We're talking maybe just a fraction of 1% of deformation over an entire decade. Because if your creep strength is too low, the equipment will eventually distort beyond repair and totally fracture.
So, we've covered the complete anatomy of a material, from basic stress and strain all the way up to dynamic fatigue and creep. Here is the final thought I want to leave you with today. If 95% of all real-world mechanical failures are caused by dynamic loads, which of these 12 properties will dictate the survival of your next design? Will it be toughness? Or maybe the endurance limit? By keeping this cheat sheet in mind, you won't just be passing your tests. You will be designing machines that actually survive the real world. Thanks for joining me on this explainer, and I'll catch you next time.